Hi, I'm Krish. I'm here to talk about our work on multimodal AI and some of our recent progress in that space. So we're going to start by calling out the fact that healthcare is multimodal. Providers need to work with a wide array of data sets and data types, from medical images to reports, lab tests, and distill relevant context from all of these during the process of care. Any individual modality is complex in its own right, magnifying the challenge of making sense of large quantities of information. For example, a chest X-ray alone can capture almost 3,000 disorders by some counts. And when it comes to AI systems, even for a single condition, training a neural network has required tens to thousands of images and examples to actually be able to approach state-of-the-art performance. To address these challenges, we released a foundation model last year to help enable researchers to train their own custom chest X-ray models using less data and compute, including rare conditions for which they may only have hundreds of images. In fact, we published examples of models that we were able to train off of this foundation model on small sets of images, including one trained on just 45 images to achieve radiologist-level performance for tuberculosis screening. As we mentioned, healthcare is multimodal. And part of the job of radiologists is to take images like X-rays and convert them into text-based reports. The advent of large language models, in particular, has captured the imagination of what could be possible in this kind of a multimodal setting. So, how do we bridge the gap between these medical foundation models and large language models to enable novel multimodal capabilities like language AI interaction? And can we do this efficiently? Our chest X-ray foundation model is large, on the order of 500 million parameters, and our large language models are also large, on the order of tens of billions of parameters or more. One of our key insights was that we could keep our foundation model and language model fixed and merely train a lightweight adapter between them, thereby reducing the resources required to create a multimodal system. What the adapter does is its job is to convert the output of the foundation model into an input context that the large language model can understand, thereby enabling us to query that LLM for context about the underlying medical image. The resulting system, which we call Elixir, enables language-based interaction with these foundation models and is state-of-the-art on a number of tasks, including zero-shot classification on conditions effectively without requiring any additional imaging data. How did we do this? Our approach was to construct the adapter in two stages by applying a well-understood technique in the literature called blip2 to our use case. In the first stage, given de-identified data set of images and reports, we leveraged the frozen version of our chest X-ray foundation model and trained a lightweight transformer called a Q-former to extract vision language features from the X-rays. In the second stage, we trained a small MLP, a fully connected neural network, to tokenize the output of that Q-former in the first stage so that it could be fed into the LLM. Both the first and second stage models that form the adapters are significantly smaller than the image encoder and large language model together, enabling training to be significantly less resource intensive and significantly more efficient. It's also worth noting that our foundation model and adapters are trained just on the images and reports, with no additional labeled data required. In addition to zero-shot classification, we've demonstrated that Elixir also enables a number of rich human-AI interactions and have benchmarked it in a few different scenarios. One is visual question answering, in which we ask Elixir questions about the X-ray and have been able to benchmark and quantify its performance there and its accuracy in that setting. Another is radiology report quality assurance. So you can imagine kind of a grammar check or a spell check for a radiologist, in which what we did was we effectively tested Elixir's ability to find errors in radiology reports, some of which we preserved as is, others of which we changed to see if Elixir was able to capture those errors. And finally, semantic search, in which we use text queries to query a database of images based on the image data alone to see and test how Elixir could actually retrieve the right images. These results are really tantalizing and demonstrating the possibilities that are emerging as modeling enters into this multimodal world. Zooming out, Google has broadly been experimenting in the space of multimodal medical AI, and the medical information adapters in the Elixir work represent one result across a larger field. One of the things that we've discovered in the process of all of this research is that the adapter method that I just mentioned for chest x-rays can also be applied to other modalities. For instance, in a paper published earlier this year by Belyeva et al., we've demonstrated how adapters for spirograms and lab values can be connected to large language models to predict asthma risk. We're going to continue to experiment with different multimodal approaches going forward, but are really excited by the prospects. To conclude, healthcare is multimodal, and our hope is that by applying these techniques across a range of modalities, we'll be able to unlock AI's potential to further assist in this space. Thank you.